All right. Happy belated Thanksgiving. Did you guys have a good break? Good food? Nice. Good. All right. Today we're going to finish up pretty much our last lecture for the course material. Thursday we'll go over the kind of exam review and go over the fourth homework. So that's due on Thursday. I think there's probably one last participation assignment that's posted. I don't remember when I put that due, probably today or Thursday or Friday or something like that. So check Moodle for that. Yeah, so last time we left off talking about what happens to dissolved oxygen downstream of a wastewater discharge, right? Where does this BOD go? What happens to stuff later? And we kind of drew up some slides to say that the oxygen content, if we can imagine some saturation level up here, the oxygen content would typically do something like this, and we'd call that an oxygen sag curve. Meanwhile, the actual substrate stuff, the thing that's demanding oxygen, would look something like this. It's just decaying over time and being consumed, and that's what's causing the deoxygenation. We also noted that we can define some oxygen deficit at any given time as the difference between the current DO, so if this guy's the DO, and this is the DO at saturation, this stuff is the BOD or substrate. Then this here would be called D for deficit. So that's the oxygen deficit. And we wanted to take a look at that in part because the deficit is what drives oxygen back into the water. So if you recall from, generic physics or thermodynamics, if you have a system that would like to be at equilibrium and then you push it away from equilibrium, it tries to get back to equilibrium, right? So that's kind of what we're doing if we consume oxygen, but the water wants to be in equilibrium with the oxygen in the atmosphere. There's now a driving force due to that gradient, or that differential, will create a gradient which drives oxygen into the water. Okay, so that lets us understand something about how much oxygen is in the water. If we can know the deficit, then we know what driving force do we have for oxygen to go back into the water. So as you might tell, might be able to see, ultimately what we're aiming at with this whole analysis is to understand what kind of deficit do we have at different times, right? And how bad does it get at the worst time? So anytime we have a discharge like this, we will typically have one spot in our stream or river, because again, we're kind of modeling this in let's say a river. We discharge wastewater into a river, it's flowing, so it's kind of like a plug flow reactor. At what point is the oxygen going to be at its worst place? Because that critical point, or that maximum deficit, that's the point where we have to make sure that biological life, all of our ecosystem services, the things that we want to maintain are still good, right? That meets our criteria of protecting intended uses. So we want to design our system to make sure that at that deficit, we're not killing fish, basically, right? We're not harming certain parts of the environment. And this is the way we want to, we can tell if that's going to be true or not. So with all of that, we can dive into the math that will get us to some sort of equation to model that. All right, so first of all, how quickly is the BOD itself being removed, or the substrate? And we're going to introduce a term here that can be a little confusing, because we talk about BOD as we In the BOD test, we give it typically 5 days and then we check it, right? So that's the BOD consumed after some time. Well, we're going to define the BOD remaining as L subscript T. So LT, that's going to be the amount remaining at a particular time. So if we draw our BOD changing again, we could say, maybe this is 2 days. We have some L at 2, and we could define that's how much is remaining, how much BOD is still remaining at the 2-day mark. This can get confusing with the way we talk about BOD, like a BOD 5 or something. Let me try to clear that up. The L naught at the very start, we're going to say this is the curve here. That value here, that's L at time 0, that's the total amount of BOD that could ever be removed or ever be demanded, if we're talking about that oxygen demand, if you gave it an infinite amount of time. So that's the ultimate BOD. So this is like that's BOD at infinity. So that would be BOD if you gave it, a full year, and then practically it doesn't change anymore because it's all the biological action has happened, right? We don't actually have to hold it for infinity, but you get the picture, right? It's basically anything that we would ever measure. That's what it is. Okay, so that's L naught here, BOD remaining at time 0, or ultimate BOD. So that means that if we were to take that 2-day measurement, that would probably be the exact same thing, or what we would notice is if we measured the difference between here and here, that would be a 2-day BOD test. How much oxygen demand was exerted in 2 days. But again, typically we measure in 5 days. So what we would do is we would measure the 5-day BOD here and the 5-day BOD here, and we could get some numbers there. So try to separate the timing out from that. The method that we can measure BOD is perhaps a little different than what we're literally talking about, how much or degradable stuff is there. So what we care about with L is how much degradable stuff is there, and that changes over time. Okay. The fact that that changes over time means that the amount of oxygen demand, the rate at which de-aeration is happening, changes over time. Okay. So the rate at which oxygen is removed will change over time, and that's why we want to know how the amount of degradable matter changes over time. So we get dL dt, so the rate of change of the amount remaining. We could write it ds dt if we're going back to our substrate terminology, right? That would be pretty much the same thing if we call it substrate. Would be equal to negative k LT. So we have a few k's to deal with. This is the rate constant for BOD removal, BOD reaction rate, and we'll have that in per day. Okay, another thing to note is that at any point we could say that the ultimate BOD is equal to LT plus however much oxygen had been demanded up to that time. So when I say the ultimate BOD is the amount remaining plus BOD, that's what I'm referring to as remaining with the L and already demanded with the BOD. So it's already been removed or processed, right? Okay. Last thing to note is that when we talk about L naught, what we're really referring to is in the case of a river with a wastewater discharge, what we're referring to is immediately after this, we're assuming it mixes, this is the L naught right here. So the river is flowing, and we have a Q for the river and a Q for the wastewater. and the L naught occurs directly after that. So that's at this point is L naught, assuming it all mixes, okay? So we're going to use the L naught in particular. As we'll see, it kind of gets built into some of the equations for how we can model the dissolved oxygen. So we're going to come back to that. We will also kind of talk a little bit more about this K and how that works in practice. So when we want to model, we now have some understanding how the actual substrate changes, but how does that affect the deoxygenation rate? Well, if we define the rate of deoxygenation, we could end up deriving something that's pretty close to, like it's dependent directly on the BOD removal, right? BOD removal corresponds directly. So we can describe the rate of deoxygenation, RD, as we'll use a new constant, the deoxygenation rate constant, and say this is going to be KD times L naught times e to the minus KDT. So it's going to be very similar to if we took if we integrated this guy, right? It's very similar to this, but we've changed it to be the rate that oxygen is changing. So we add in a little bit extra there. Okay, so we're going to take that rate as, we're not going to do too thorough of a derivation there, but that's our rate for deoxygenation. And now we need to find, okay, well, what about reaeration? So we got that part defined. Well, the reaeration, this is essentially going to be a physical process. You can think about even just bubbling water through a wastewater treatment plant, right? It's physical, that gas transfer. Think about a waterfall, a fountain in a pond. It's very, very much a matter of mixing the air with a high surface area in contact with the water, right? So a waterfall is going to have a lot better reaeration than a stagnant pond, okay? So it's going to be physical, and it's also going to be proportional to the oxygen saturation level and the oxygen deficit that we happen to have given the fact that oxygen has been removed. Okay, so the more deficit, the higher the gradient pressure to push oxygen into the water. So if you have 0 oxygen in the water, it will be reaerating fast comparatively. If it's very cold water, which would increase the saturation, it will reaerate faster. So if you have low saturation level, or if you have not much deficit, your reaeration won't be super high. Okay, so then we can describe our reaeration rate simply as this is a positive, right? This is a growth equation, Kr times the deficit. So that's why we're talking about deficit. Keep that distinct in your mind, different than the dissolved oxygen, right? So deficit, I think we talked about it, or no, I have it written right here. The deficit, D, is the dissolved oxygen at saturation minus the current dissolved oxygen, okay? It's pretty simple, but it is also simple to confuse it, right? Because there's lots of D's and O's and all that, right? So you could even, if you wanted to, call it OD for oxygen deficit, and then it gets even more confusing probably, right? OD, DO, what are we talking about? Okay, so then this reaeration rate constant, again, this will be in a per time unit. We're going to say it's in days. And then we have a formula to calculate Kr based on some characteristics of the river. Now this is going to be a strange type of equation because it's strictly empirical, meaning people made a bunch of observations in the real world. Okay, here's a river, here's the temperature, blah, blah, blah. What's the reaeration rate constant? Like, you could solve for that taking enough data. Right? They set up experiments to test that, different parts of the river, how deep was it here, how fast was it here, probably measured some other parameters, but they were able to consolidate it down to just depth and speed to give us some indication of how quickly the reaeration happens, right? Shallow water has a lot of surface area, and most of the water is exposed to the air, so that reaerates better. Fast water tends to be turbulent, tends to bounce around, maybe splash, maybe we're talking about like rapids. That will tend to be better at reaerating. So the units here are not going to work, but that's okay because it's empirical. This is not a theoretical. This doesn't come from some derivation of math. You know, this is just, they got a bunch of data and made some lines of best fit. And they did that with 2 variables and put all that together to get it in terms of the speed and the depth. Okay, so this equation down here, we are going to input meters and seconds in terms of speed and meters in terms of depth, and we're going to get out per day units magically. Okay, that's just the way it is. So we're going to have per day despite the units. So this is one time the units are not going to match. And we'll just say that's it's because it's empirical. Okay, so that gives us an equation, however, to get Kr given some facts about the river or stream. All right, that's the point. So then we can take the rate now that we have for deoxygenation and the rate we have for reaeration and solve that to find our dissolved oxygen, or at least our deficit perhaps. Might be easier to work with deficit at first. Our deficit as a function of how far we've gone downstream. But first, we were talking about K for the BOD reaction rate constant, K with no subscript. And then we went on to KD, and I didn't really mention any difference there. So let's take a look at what the book says about that. So turns out we can usually treat them the same. It says here the rate of deoxygenation at any point in the river is assumed to be proportional to the BOD remaining. So that we talked about that already. And goes on to say the deoxygenation rate constant KD is often assumed to be the same temperature adjusted BOD rate constant K obtained in a standard laboratory BOD test. For slowly moving rivers, this seems to be pretty reasonable, but when it's turbulent or rapid, that's not quite so much. But in general, we can kind of just take K to be KD, is ultimately its point. Perhaps there's something we could do to, stir the laboratory situation a little more rapidly or something. But in general, that's the situation. And so for our purposes, we're just going to use KD. All right, so just a quick visualization of when we're talking about that physical difference between like a slow-moving stream versus rapids and waterfalls. Here are the Kr values, or the ranges typical for these. And we could get this, we could define this from that equation we had, right? That had something to do with the velocity and the height. I think it was velocity to the 1/2 and 3.9, velocity to the 1/2 and height to the 3/2, something like that. So we could find each piece here essentially from that. But just as a quick reference point, our small ponds and backwaters, really pretty stagnant stuff, 0.1 to 0.2-ish per day is the rate constant, whereas rapids and waterfalls are 1.15 or higher. So that's just kind of a visualization of how much these parameters will vary, and we'll see something between those ranges as we do some practice problems. All right, so we basically have all the pieces now, and I just want to take another look here to actually look at the rates. What we drew earlier in this type of a plot was kind of the amount of oxygen, the amount of deficit, the amount of substrate. Well, here at the upper point, we can see the rate, and on the bottom, that's the amount, right? So that's the oxygen sag curve here. So we'd have some, saturation point up there. So if we look at the top, though, we can see the rate, and the rate of deoxygenation, that's proportional to how much substrate's there, right? So that's just going to decrease the whole time. That's this guy. The rate of reaeration is going to be getting faster and faster as we have more and more deficit. And then as we reach that minimum point for our oxygen, then the rate of reaeration turns around and starts slowing down. So we can see this rate of reaeration. It starts off low because generally typically we'll aerate our wastewater before discharging it. So typically it's not going to have a big immediate impact on our river, but then the BOD will be consuming oxygen, and that oxygen that's there will be decreasing, causing that reaeration to increase. So typically we start low with the rate, and then we raise up to a point, and we reach the highest point at the exact point where our deficit is the largest. The oxygen is the lowest. So we'll notice here that this point matches the exact same time as our critical point, TC, as it's labeled, or XC, and that's the moment that we kind of concern ourselves about the most in terms of the potential impact. Okay, so then of course the rate of reaeration slows down as the oxygen actually comes back up and there's not much deficit anymore. Okay, that makes sense? All right, so if we want to model the deficit itself, we could say DO or D naught is the initial deficit. D would be the deficit at any time T. So DD, DT, we can define as the rate of deaeration minus the rate of aeration. So, deoxygenation minus the aeration. So deficit, it's a little hard to think about, right? Deficit is a negative, so the deoxygenation is a positive for deficit. Reaeration is a negative for deficit. So it feels a little backwards, but we can define the rate of change for the deficit in this manner. Okay, so the deficit grows. It's a growth reaction if we have deoxygenation happening. Okay, so earlier we defined the rate of deoxygenation here and the rate of reaeration here. Okay, so we get that in the form of dd dt equals kd L naught times e to the minus kt. And this could be, go ahead and put kdt, minus kr times d. All right, so take a moment to integrate that. Just kidding. None of you are even looking at me smiling here. That would be a little bit difficult, I think, right? Trying to integrate that. All right, so the book will do it for us, thankfully. I don't want to do that. So here's the integration. We can get this in terms of the initial deficit and the amount of stuff we have there, L naught, at the start, and in terms of T and all these constants. So it turns out we can get it in a pretty reasonable form in terms of knowing the different components. So we have KD, L naught, KR, here's KD again, the time, T, and the initial deficit. Those are all the parameters, right? So one variable is time, and all of these constants that we've kind of already talked about. So that will be given to you on your formula sheet. The task will be to recognize what's KR, what's KD, how do we get these pieces, right? And how would we define the initial deficit? Things like that. How do we define the initial L naught? And those are going to be typically from the problem. We'll start there on some practice in a little bit. Okay, so that's the integration. There's one caveat here. We'll notice if by happenstance the rate constants here happen to be equal. This is not the rates, right? The rates will eventually be equal at that critical point, right? We have the same amount of oxygen removal as addition, so it's not going anywhere, briefly. But if the constants are equal, then we divide by 0, right? And we can't do that. So we'll say we got a problem if Kr equals Kd. So what do? If we encounter that problem, well, we have another equation that can approximate it pretty well. Again, the book gives us this. We're not going to bother with that derivation. This equation here will also be on your formula sheet, and you need to know that this is only for the case where those constants are the same. Your number won't be too far off, but this one's not as precise. So this should only be used if Kr is equal to Kd. Okay, so that's the stipulation here. And one thing we'll notice is that when we measure the distance and the time in a moment, that it gets a little bit tricky there because we also have a divide by 0 and we can't really use that one. So if Kr is equal to Kd, that kind of limits us a bit. We can get the deficit at a given time, but it's going to be harder to find the time, the minimum time. Okay, so about that critical point though, that's the moment that we really care about. That's the moment where if fish are happy and healthy there, then our wastewater discharge is just fine, right? Nothing worse can happen. So we'll say that xc, that's our critical point. That's the distance downstream where the deficit hits its maximum value. U is then the stream speed. Maybe we'll often use it in kilometers per day in this case. Tc would be the time elapsed between that discharge point, xc, downstream. That would be, again, in days. So we have an equation here, and we can connect the distance and the time if the velocity is constant, which we'll probably just assume. That's just, the velocity is distance over time, right? So it's very simple. We can convert. So we've got this critical point in time to say that's 1 over Kr minus Kd times the natural log of Kr over Kd times 1 minus d naught times Kr minus Kd, all that over Kd times L naught. So we've got this equation also on your formula sheet. Again, lots of stuff there, but it's these parameters that we've just talked about, right? So we've done all that mass balance stuff. You can kind of see how that would have happened had we had the wherewithal to integrate it ourselves. We could have done that, right? That's not too new in terms of what we've been doing all semester, right? Here's a rate, here's another rate. Let's put them together. Let's solve for the thing we're interested in, and then take some algebra to, in this case, find that point at which D is maximized or the dissolved oxygen is minimized. Okay, so I've let the book do all that algebra, all the calculus for us. Here are the equations. So then it's up to you to recognize kind of where that's coming from and how to then put it into practice. All right, make sense? Okay, so let's put it into practice. In this problem, we're going to start off a little simpler, so don't feel like we need to jump right into all those equations. We've got a table up here, solubility of oxygen in water. It's based on temperature, but also chloride concentration. So oxygen's solubility depends on a few things, chloride concentration being one of them. We'll assume that our chloride is 0. I think there might have been some sort of context from the previous problems, but we're just going to stick with 0. So this example says the wastewater in a prior example has a dissolved oxygen concentration of 2 milligrams per liter and a discharge rate of 1.1 cubic meter per second. The river that is receiving the waste has a DO equal to 8.3 milligrams per liter, a flow rate of 8.7 cubic meters per second, and a temperature of 20 degrees Celsius. So that puts us, for the plot here, the 20 degrees Celsius. It's 9.09 here is our value. Okay, assuming complete and instantaneous mixing, estimate the initial dissolved oxygen deficit. So we are told to estimate this guy. So it's a deficit, and it's the initial one, so that should be D naught, right? So estimate that of the mixture of wastewater and river water just downstream of the discharge point. All right, so go ahead and solve for that. Don't forget to draw your system so you understand what's happening, and I'll join you in a moment. All right, so in this problem, we can kind of see what we're being asked for is that initial deficit. What we're referring to is that right once we have mixed the wastewater with the river water, that's our initial point, right? What we're tracking from there is anything downstream of that. So that's kind of our initial point. I sort of drew that up with this little line right here. So once we've mixed them, now we have what's coming in. We could draw a little control boundary, right? We could say we've got two things going in, the river water and the wastewater, and one thing going out, which is the mixed river, right? It's the new river. And so putting all that up here, we see that we can find out how much oxygen is dissolved in the mixture and then compare that to the saturation value to get our deficit. So that's what I wrote here as the deficit initial is going to be the saturation value. That's 9.09 from the lookup table, minus that mixture that we need to solve for, and that's going to be our answer. Okay, so to get our answer, this is a simple mass balance here where we say what's going in is what's equal to what's going out. So we have one thing going out, that's the QM and the DOM. That's going to be equal to what's going in, which is the river and the wastewater. So I wrote it up this way. We can solve for it to say the DO of the mixture is QRDOR plus QWDO, the waste, all that divided by the flow rate of the mixture. So when we put those values in, does anybody have that already? If not, we'll do the calculator. Okay. So we have the river was 8.7 times 8.3. We're going to add to that so it's 72.21. And that was 1.1 times 2. So that's 71. I say 71.21. I think. Divide all that by our Q of the mixture, which was 9.8. So 7.49. milligrams per liter. So that should be our new dissolved oxygen concentration of the mixture, and that is below what the river itself is. The river had 8.3, so it should have some drop there. It should be higher than the wastewater, and it just given that it's like 1.1 of one and 8.3 of the other, or 8.7 of the other, yeah, it should be closer to what's in the river, right? There's more water in the river, so just physically this makes sense. It's closer to the river value than the wastewater value. Okay, so that means then our our deficit, D naught, should be that 9.09 minus 7.49 should be 1.5 milligrams per liter. Okay, does this make sense? So in this case, we're kind of just setting up the problem, recognizing what goes where and how the pieces might fit together. All right, so now we'll kind of expand from there and make use of the larger equations that we were talking about. So just below, this is the next example, just below the point where a continuous discharge of pollution mixes with a river, the BOD is 10.9 milligrams per liter. And the DO is 7.6 milligrams per liter. The river and wastewater mixture have a temperature of 20 degrees Celsius. Again, we're going to assume no chloride here. So we'll use the same value, 9.09. A deoxygenation rate constant, KD, of 0.2 per day, average flow speed of 0.3 meters per second, average depth of 3 meters, and that's kind of according to a previous problems. Okay, then it says find the time and distance downstream at which the oxygen deficit is at a maximum. That's part A, and B is find the minimum value of dissolved oxygen. Okay, so part A is looking for the critical time and the critical location or distance, and then the DO minimum. All right, take a few minutes to work on that, and we'll work together on it in maybe 10 minutes or so. Feel free to ask questions along the way, and or work together.
units don't matter for like KD per day. Am I using seconds or days?
KD should be in per day. I would suggest doing everything in per day. The only thing is when you calculate KR, don't worry about these units.
Okay.
Just leave that in per day.
So when you calculate the time, the critical time, it would be in days.
Days, yeah. All right, so you've seen I've started the process here and gotten partway through. I'll show you in Excel in a moment what I've been working on. First, I really wanted to just kind of get a lot of the basics that I knew we would need. Part of that's from the problem, and part of that's from just calculating stuff. So we have the initial deficit should be the DO of the mixture just downstream that was given to us here, 7.6. The difference between that and the saturation value, right? So that's the 9.09 minus 7.6. That gives us that value. KD was given at 0.2 per day. KR we can calculate from this guy up here, KR. We were given the stream height and the stream speed in meters and seconds. So that's the magic that gives us per day units, the one time you should not pay attention to units. Yeah.
For this one, it should just be kilometers, not kilometers per day.
In terms of the, which part?
For U or XC.
For when we solve for XC, I was setting up to solve in kilometers. You could solve in meters and then, or whichever, but I was setting this up so that because I solved for TC in days, I went ahead and started converting. So here's the next step. I found TC by putting all of these pieces into our equation for TC. Just real briefly before we get there, the BOD, it said when it mixes is 10.9. So maybe a little vague there, but we can just say that's what it is at that moment, right? So that would be the starting moment. So that should be the BOD remaining at time 0. That's the ultimate BOD, okay? So we're just gonna use that. There's no other piece that we really could work with there. So that's our L naught 10.9. So we put all of these into our large equation there for our time. And we should get, this is me entering all that in there. And that brings us to that 2.68 days value there. And from there, we can go on and say, okay, well, we've got 2.68 days. The XC then should be the time times the speed. But the speed right now is in meters per second, so we need to convert one way or the other. You could convert the days into seconds if you want. I was going to just go ahead and convert the speed into kilometers per day. So multiply by 86,400 seconds per day, divide by 1,000 meters per kilometer. And we'll get a new speed that's 25.92 kilometers per day. And when we put those together, we can get this value of 69.3 kilometers for the X value. Okay, so that gives us almost everything. So now we need to find the minimum value of DO. And here we need to find, what we can do is solve for the deficit at the time at which we're at the critical point. Okay, so we're going to take the time where we found the critical point and then use the other equation to solve for the deficit. So remember that this guy here is only for the special case where we have KR equals KD, so we're not going to pay attention to that one. We'll use this guy, and we have everything. We just need to put in the value of time that we solved here, 2.68 days. So I'm going to take a moment and do that and get the final answer for you. Should not take too long because I've got everything in here. So this will get us the maximum deficit, but from there we want to take, if we need to find the saturation value or the actual dissolved oxygen value, then we need to take an account for the deficit, right? So two steps here. The major step is to take this first part. So it would be KD times L naught divided by KR minus KD times E to the negative KD times our time minus E. I guess I should have done that, right? Oops. Okay, it'll take a little longer if I just erase it every time. Okay, so our deficit, max deficit should be 3.1 milligrams per liter. If I entered all that right, seems like a reasonable number. Yeah, get something wrong?
Back on a couple, like one of the beginning ones, why don't you just set the accumulation equal to 0? The equation's like a couple of terms, and you get the same thing.
Why don't I set what to 0?
So for the modeling the 2 deficit, the accumulation equal to the deoxygenation rate minus the reaeration rate. If you just set the accumulation at 0 and solve for D, you have an equation that's less cumbersome, and you get the exact same thing.
Ah, so instead of using the, because this one is, you're solving it in a case where the rates have equalized. That would be a, yeah, I think I see what you're saying. Let me try to explain what wavelength you're on. Okay, so I was just taking this equation, which the book gives us, like, hey, you can find the deficit at any time. But the smarter thing to do would be to say, hey, well, we could say that at that critical point, the rates are equal, right? The rate of aeration is equal to the rate of deoxygenation. That's kind of what you're saying. So you can actually get a simpler form and solve for the deficit at that point, right? And solving that out here, let's see, what the terms themselves, the rate for deaeration was KD L naught E to the minus KDT, right? And the rate of reaeration was simpler. This was KR D naught? KR, was this D naught or just a generic?
Just
D. Drop this negative. Okay. Yeah, so when those rates are the same, we could then solve for D that way. Simpler. I like it.
Would you use just the critical time?
Yeah, you'd use the critical time there. This would only be for the case when those rates do equalize. So if you're tracking all that and you know the difference, fantastic. That's a great insight there. It's essentially this simplified for the moment where we're at that critical point. You're always safe to use this equation otherwise. In fact, is that the same thing? No, that's not quite the same thing. Okay, so good call there. So with this deficit one way or the other, that should be the max deficit, then we can say that, you know, given that a deficit is equal to the DO saturation minus DO current at some time, we'll say T, we can solve for DO T by taking, putting that to both sides and subtracting the deficit from the saturation. So that means our dissolved oxygen at Tc is equal to this, let's see, saturation was 9.09 minus 3.1, and don't feel like doing that in my head. Oops, what did I do? Okay, 5.99. It should be our dissolved oxygen at the end of all that. Okay, so this guy is a little caveat. So just, if you're going to look at that, only consider that for the moment where the deficit is, you've hit that critical point where they're equal. Okay, so make sense? Good on that? All right, so that's all I've got for you. We'll see you on Thursday.